this session. In this session, we shall discuss about the question: can we define an order on C? Can we define an order on C? So the initial theory we know that is R is an ordered field. R is an ordered field. That is, R is a field. R is a field on which there is some order. Right? So usually we know that R is a field. On that field we can impose some order. And for example, less than. So usual less than relation. So this usual less than relation will be an order on R. What do you mean by order? So order means it is a relation. It is a relation R which satisfies two conditions. One is transitivity, and the other is law of trichotomy. So any relation R on a set, which suppose R is a relation of A, then R is said to be transitive if any three elements of A. If A is related to B, B is related to C, then A should be related to C. Right? And law of trichotomy is, so given any pair of elements of A, either A should be related to B or B should be related to A, or A and B should be equal to B. Right? So any relation on a set A is said to be an order if it is transitive and it satisfies law of trichotomy. Now on the set of all real numbers, impose less than relation. Then obviously it will be transitive and it will satisfy law of trichotomy. For it, if A, B, C are real numbers, if suppose A is less than B and B is less than C, then A is less than B and B is less than C. So A is less than C. So it is transitive and law of trichotomy. So given any two real numbers, either A should be less than B or B should be less than A, or A should be equal to B. Any one of these three should hold, because given any two real numbers, we can mark those two numbers on the number line, whichever comes the first. If A comes first, then A will be smaller than B, or if B comes first, B will be smaller than K, or A and B should be equal. Any one of these should hold. So we can define an order on R. So this is not the only order on R. We can define greater than, we can define equals, many relations. So, but there is some order, at least one order on A, which is a field. So R is an ordered field. So like this, can we make C also an ordered field? You know that already C is a field. If we can define some order, on C, then C will also be an ordered field. Now the question is, can we define an order on C? Or if we define some order on C, what happens? Now we shall see that one. now question is, can we define an order on C? So suppose assume that we can define an order on C. That means on the set of all complex numbers, assume that we can define some order. That means a relation which satisfies transitivity and law of trichotomy. So such a relation we can define on C. And assuming, suppose there exists a relation, or suppose there exists an order. I will denote it by less than. Usually order is denoted by less than symbol. So suppose there exists an order less than on C. Then so C is already a field. On this field, now by our assumption there is an order. Then C is an ordered field. C is an ordered field. Okay. Now we know that in an ordered field, say F, if X is an element of the field F with X is non-zero, then square of X has to be greater than 0. It should be positive. So this is a property of an ordered field. We have studied this in real analysis. Given an ordered field, every non-zero element, its square has to be positive. Square of every non-zero element has to be positive. Now come to this one. So C is an ordered field. So C should also satisfy this condition. That means square of every non-zero complex number has to be positive. Now I consider a complex number which is I. I is a complex number whose value is square root of -1. Now what is this square? We know that I square is -1, which is negative. But according to the property of an ordered field, square of every non-zero complex number has to be positive. But I am writing it as negative. Here I is a complex number which is other than 0, because the value of I is square root of -1, which is other than 0, but I square is -1. So we got a contradiction. So assuming there is an order on C, we end up with a contradiction. So the assumption which we have made is wrong. That means there cannot be any order on C. So thus we can conclude that there cannot be any order on C. So that means we cannot define any order on C. In particular, we cannot define less than or greater than orders. So in general, as there cannot be any order on C, so these two, the usual less than and usual greater than, so these two will not be an order on C, right? So by this observation, I can say that there is no notion of smaller and bigger complex numbers. As a result of this observation, what this observation says, there cannot be any order on C. We cannot define any order on C. In particular, so this less than, what we call usual less than, that is, we will say 2 is less than 3. So this less than relation and greater than relation. So these relations will also not be an order on C. If at all any one among these is an order, then it will be a contradiction to this, right? So as there cannot be any order on C, in particular these two relations will also not be order on C. So there is no notion of less than or greater than on the set of all complex numbers. So if you have two complex numbers, you cannot say Z1 is less than Z2 or Z1 is greater than Z2. Only thing is you can equate two complex numbers. I can say Z1 is equal to Z2 whenever both have same representation. That means both have same real and imaginary parts. But we cannot compare two complex numbers in the notion of lesser and greater. So hence we do not have the notion of smaller and bigger complex numbers. So given a complex number, you cannot say it is less than another complex number. So this is about order on C. So there cannot be any order on C. Hence, in particular, the usual less than and greater than relations which we use on the set of all real numbers. On the set of all real numbers, it is an order. Using this relation, we can place numbers in the order. So 1 comes before, after that 2, after that 3, like this. We can place the numbers in an order. But this relation will not be an order on C. So there will not be any order on the set of all complex numbers. We cannot place the complex numbers in an order. That means this number comes first. That number comes to the next. We cannot say like this. So there are no smaller complex numbers and bigger complex numbers. So just only we can equate two complex numbers. Right? Okay, now we shall discuss an important concept on the set of all complex numbers, which is conjugate of a complex number. Conjugate of a complex number. So now what do you mean by conjugate of a complex number? So if z is equal to a plus ib is a complex number, is any arbitrary complex number, then the conjugate of the complex number z is the complex number a minus I and is denoted by the symbol z bar. So conjugate of a complex number is again a complex number got by just negating the imaginary part. So if you are starting with the complex number a plus ib, then its conjugate will be the complex number a minus ib. So by just negating the imaginary part, we will get the complex number, which is called conjugate of the given complex number, and it is usually denoted by z bar. For example, if I take z to be 2 plus i3, or 2 plus 3i also you can call it as, then its conjugate denoted by z bar will be, so how we will get, so just follow this definition. In place of a plus i3 we have 2 plus i3, that is a is 2, b is 3. So just we have to replace b by minus b. Just we have to replace b by minus b. So here b is 3, we have to replace 3 by minus b. So it is 2 minus I. So this is about conjugate. Now we can observe that given a complex number, So if I consider this complex number a plus ib, so a and b are unique. And for this conjugate will be a minus ib, a minus ib. So which will be unique for this complex number. That means given a complex number, it will have one and only one conjugate. It cannot have more than one conjugate. In this example only. So if I want to write the conjugate of this complex number, the only thing is I have to negate the imaginary part, and in that case I get only 2 minus 3i. I cannot get another complex number. That means for a given complex number, its conjugate is always unique. That means it can have only one conjugate. It cannot have more than one conjugate. So that means, so here what we are doing is, so every complex number. So in this way, I can write conjugate for every complex number. That means every complex number is associated with another complex number in a unique way. In a unique way. Every complex number is associated with another complex number in a unique way. Or you can associate every complex number to another complex number uniquely. So whenever you come across unique association, unique correspondence, then the concept of function will enter. So conjugation of complex numbers can be regarded as a function because we can regard this as a function from the set of all complex numbers into itself. So what this function is doing, it takes every complex number, it associates with again a complex number which is unique. For this complex number, this is the only conjugate. So we have a unique association of all the complex numbers into another complex number. So we can regard this association, we can regard this definition of conjugation of complex numbers as a function. Right? What is that function? So the conjugation of complex numbers can be regarded as the function f from C to itself, right? Because what this conjugation is doing, it takes a complex number and it associates to another complex number, because there's a complex number form, so it associates to another complex number defined by, what is the definition of this complex number? So given any complex number a plus ib, its image is associated to the complex number a minus ib. Or if I take the notation z is equal to a plus ib, then f of z is z bar, because if z is equal to a plus ib, its conjugate is a minus ib, which is denoted by z bar. So this function is f of z equals z bar. And we can verify it is a well-defined function. The well-definedness just follows by the unique association. So what do you mean by well-defined function? So well-defined function means it is just verifying the definition of the function itself. So that means every domain element has to be associated with one and only one element. And it is true in this case. If we consider any complex number, it is associated to one and only one complex number. So this unique association will directly imply the well-definedness. So whenever we have a function, we can talk about one-one-ness and onto-ness. So now what about one-one function here? So is f is 1 1 that f is 1 1, what I have to do? So the definition of 1 1 function is if images are equal, the elements has to be equal. So start with two elements of domain. So let z1 equals a1 plus ib1, z2 equals a2 plus ib2, be into complex numbers. Then suppose f of z1 is equal to f of z, f of z. Then that is f of a1 plus ib1 is equal to f of a2 plus ib. According to our definition, what is the image of f of a plus ib is a minus ib. That is, it is a1 minus ib1. It is a2 minus ib. Right? Or that is, I can write it as a1 plus ib into minus b1. So just combine this minus with b1. It is a2 plus I into minus b. Now what we have? We have equality of the complex numbers. So these two complex numbers are equal ways. Real and imaginary parts has to be equal. So a1 has to be equal to a2 and minus b1 has to be equal to minus b. That is, b1 has to be equal to b. So a1 is equal to a2, b1 is equal to b2. So that means a1 a1 plus ib1 will nothing but a2 plus ib. So as real and imaginary parts are equal, complex numbers will be equal. So if the images are equal, the elements are equal. So I can say f is a 1 1 function. F is a 1 1 function. Now you have to check ontoness. So onto means for every codomain element there should be an domain element whose image is the given element. So start with a codomain element. Here codomain is also C. So start with a general complex number. Now we have to search a domain element whose image is a plus ib. So here image means, so just will negate its imaginary part. So ಯಾವ ಕಾಂಪ್ಲೆಕ್ಸ್ ನಂಬರ್ ಅನ್ನ we consider ಮಾಡಿದ್ರೆ ಅದರ image a plus ib ಬರುತ್ತೆ ಅಂತ ನೋಡಬೇಕು. So when we get a plus ib, so then consider a minus ib. So the complex number a minus ib such that, so what is its image? What is its image? So images, so just have to negate the imaginary part. Here the imaginary part is minus b, its negation is plus b. So a plus ib is nothing but 7. So for every codomain element, we found a domain element because domain is again C. So we found a domain element such that its image is the given element. So which shows that f is onto also. F is onto also. So f is both 1 1 and onto. So f is a bijection. F is a bijection. Okay, by this I end the session. In the next session, we shall see some of the properties of the conjugate function.